Let's prove the convergence of the Jacobi iteration. What is the Jacobi iteration? It's the brother of Gauss-Seidel iteration. Gauss-Seidel is a little more complicated to prove, so we will focus on Jacobi. Jacobi is the brother. It's not a real life brother, but in the sense of this algorithm, it's very, very similar. First, I want to explain what is Jacobi, and then we see it's quite similar to Gauss-Seidel. And then we will prove that Jacobi iteration will converge if the coefficient matrix is diagonal dominant. Okay, let's start with Gauss-Seidel, what we already know. Please give me a matrix, let's say 3 by 3, some arbitrary matrix, but it should be diagonal dominant, and then we can use this matrix as an example. Okay, maybe you give me 6, 3, minus 1. 6 is more than 3 plus 1. Okay, then the second line, 5, the element on the diagonal is more than the others added. And maybe the last line you will give me 4, 1, 8, 5 is less than 8. So this is a diagonal dominant matrix. Okay, then we have the unknowns which you want to find, and then give me some right hand side. It doesn't matter which one. Okay, 1, 2, and 7. What is Gauss-Seidel? How does it work? Okay, we start with an arbitrary vector. If we know nothing, then let's start with the 0 vector, most easy vector of all. Then we go into equation 1, that means line 1, and then we assume x2 and x3 are already correct, so in this case 0, 0. And then out of line 1 we can get x1 like we do when doing back substitution. Okay. What do we do? Okay, we take the right hand side, so x1 is the right hand side, and then we bring everything on the other side. So we bring 3 times x1, x1 here is 0, and we bring minus 1 times x3, and this is also 0, and then we have 6x1 is equal to that, and x1 we have to divide by 6, and in this case this is 0. 1 divided by 6, and as a decimal number we get this number. Okay, this was equation 1, and then we update here the first coordinate, and so we get. Now we go into the second line, the second equation, and we do as we did here, but now we assume x1 and x3 to be already correct, and then we get x2 out of this equation. So what do? We bring everything to the right hand side, 2 is still there, and then we subtract x1 and x3, so 1 times x1, 1 times 1 over 6, plus 2 times x3, and this is in the moment 0. And then we divide, we have 5 times x2, we want 1 times x2, so we have to divide by 5. This is 2 minus 1 divided by 6, that's 11 divided by 6, divided by 5 is 11 divided by 30, and as a decimal number this is this one. Okay, then we update that x, we update the second coordinate 0.1667 and 0.3667 and a 0 in coordinate 3. Then we go to equation 3. Here we update x3 under the assumption that x1 and x2 are already correct. So we have a 7 minus everything to the other side. So 4 times x1 and 1 times x2 and divided by 8. And using your electronic calculator, you will get this number. So we can update the third coordinate. In this case they are all between 0 and 1, but that's up to that example. And now we updated each coordinate once, and what do? We start over now using that instead of that, and then out of equation 1 we will once more update x1, and after that we take that result, exchange that number, then we update x2 out of this equation, and so we iterate and iterate. and we do that till all digits stay the same or something like that. So this is Gauss-Seidel, and it is guaranteed that this iteration converges to the correct solution if the coefficient matrix is diagonal dominant, which is the case in that example. Okay, we want to prove Jacobi, not Gauss-Seidel, because it's more easy to prove. And now I want to show you what is Jacobi. It is almost the same algorithm. So again, we have this problem. And then we start again with some arbitrary solution, which is not the solution, but it's maybe close to the solution. We will iterate, we will improve that solution. So we go into equation 1 and we do the same. We update x1 by the assumption that x2 and x3 are still correct. So we'll do exactly the same. Okay, and now we will not update that one till one whole run. We keep that first assumption and then we will update at a whole. So, okay, we go into equation 2. We are using equation 2 to update x2. And now things will change a little. Now we have 1 times x1 and we use that one. So we have 1 times 0 plus 2 times x3. That's again a 0. And then divided by 5, and so we get 2 divided by 5, which is 0.4. Then we go into equation 3, and under the assumption that x1 and x2 are correct, we calculate here x3. So x3 is 7 minus, and then 4 times x1. x1 is 0, 4 times 0, plus 1 times x2, which is also 0 in the moment, and then we divide by 8, and so we get 7 divided by 8, and that's 0.8750. And then we do the update, and then we iterate again. We take that to be here, and then we update. Then we have 1 minus 3 times that, plus minus 1 times 875 instead of 0. Then we go into equation 2, 2 minus 1 times that plus 2 times that. And then we go into equation 3, 7 minus 4 times that plus 1 times that. And then we get a new x, and then we do that again and again. So there's a very small difference. Okay, we hope that the solution will converge, and we will prove that it will converge if the coefficient matrix A, this one, is diagonal dominant. And so it is likely that this is a better number than that was. So it's not a good idea not to use this improved number. That was my feeling when I first heard of Jacobi. So what can be the advantage of Jacobi? The first advantage is it's more easy to prove, but there's a second advantage. Indeed, a second advantage, and this is you can parallelize this. So if you have 3 cores, every core can do one calculation, and here you cannot parallelize because this update must wait to this number, otherwise it can't start working. And so for parallel computing, Jacobi would be maybe the better idea. Okay, this is Jacobi and this is Gauss-Seidel, and we will prove that Jacobi will converge to the solution if the coefficient matrix is diagonal dominant. And what will we use? We will use things we did in the videos before. There we prepared the field, so now we can do that proof. What will we do next? We will reformulate that algorithm more in the language of matrices, and then we can use the matrix calculus to do some operations on the equations, and then we'll see. Okay, let's reformulate Jacobi. We can write the coefficient matrix A as the sum of a diagonal matrix and the rest. Why do we do so? We will see later. Let's do the example. And then we can write that as 6, 5, 8 and zeros plus the rest. And that is our matrix D, and that is our matrix S. Okay, and then what is the update of the x vector? The x vector is updated by take the right hand side B and subtract everything in each line except of the diagonal. So this is that S, everything but not the diagonal. So we can write B minus S times X. Okay, that is this. Okay, 1, 2, 7 is the right hand side B, and this 3 minus 1 is that 3 minus 1, 1, 2 is that 1, 2, and 4, 1 is that 4, 1, and these zeros imply that this multiplication is omitted. Okay, and then we have to divide by 6. How can we divide by 6? We can also multiply by 1 divided by 6, and that we can write by the inverse of D is 1 divided by 6, 1 divided by 5, and 1 divided by 8. This is only true for diagonal matrices. We can normally we can't invert by doing so, but for diagonal matrices we can. And so we can multiply by D inverse. Why is that true? Because a diagonal matrix times a vector multiplies each element with the diagonal element. So we can reformulate that way, and normally we say, okay, this is x1 and this was x0, so we get the new x vector. Or more general, in the nth step we have that. So we can write that here in our example. Xn is D inverse times right hand side minus S times the xn minus 1. And now we have our iteration process. We have a new x version out of that evaluation, and then we take that new version as an input here and get the next and so on. So we can formulate it f of x with that function doing this operation. So this is the iterating function. No, that was incorrect, and now we can write that way. And what will we do next? Next we will prove that f is contractive, and if this is true, then f has one fixed point, and then the fixed point is the solution of the system. Okay, what do we have to show? We have to show that the difference of the image. So what is f of x and f of y? And now let's expand. D inverse times b. D inverse times b again. So this cancels. We can factor out, and so we get this version. So if we take the norm of that, and let's take the maximum norm, then we can write it here. So this is a matrix, this is a vector. If we take the maximum norm and the row sum norm, because they are consistent, we can do the following. D inverse times S, the matrix row sum norm times that y minus x, and this is the same as the other way around. And now we are here, and here we have a constant C, and now we will show that this constant C is less than 1 if the matrix is diagonal dominant, and then we can apply Banach fixed point theorem. So let's examine that. This is our D inverse, and this is our S zeros on the diagonal. And what is that product? If you have a diagonal matrix to the left and a matrix to the right, then every line, every entry of that line is scaled by the corresponding entry in the diagonal matrix. So we get 0 divided by 1, 1, which is 0, and then this entry divided by that, and then the next entry, and then all these entries. And the same in the second line. Now the line is scaled by that entry. This is D inverse times S. Maybe it's easier to understand if we do that for our example. And then we have, and every line is scaled by that element. So 0, 3 divided by 6, and minus 1 divided by 6, divided by 5, 0 here, and 2 divided by 5, and in the third line 4 divided by 8, 1 divided by 8, and the 0 here. So this is D inverse times S. And what is the row sum norm of that matrix, of that matrix, of that matrix? What is the row sum norm? We can add, so we get 4 divided by 6, 3 divided by 5, and 5 divided by 8 in this example. And that means the row sum norm, what was the largest number? It was this one, 0.6666 compared to 0.6 compared to 0.625. So this was the largest sum here. And we are always below 0, because if we add these, then we have the same denominator, and the nominator, if we sum that, it's always, due to the fact that it's diagonal dominant, this sum is less than A11, and if we divide something which is less than A11 and then we divide by A11, then we get something below 1. So this row sum norm, the absolute values, will be 100% sure a number less than 1. And that implies that we have and that means so the iteration must converge to the fixed point, and all what we have to show is this fixed point is the solution of the system of linear equations. There is not so much space, so allow me to write it. Here. Here is some space. The fixed point means that x is the same than d inverse times b minus s times x, and then we can expand, and then let's multiply by d. D times d inverse is identity times b is b, and here again the same, and then we can bring that to the other side, and then this is a, and so we have a times x is b. So the fixed point of f is the solution of the system. And so we are done, our proof is done. So this was the proof of the Jacobi iteration. That was mathematics, hardcore mathematics, but I think it's really fascinating, and I think if you want to earn a master's degree, then you also have to go a little bit into the mathematics part. And here this is a very good example. Mathematics introduce a concept of norms and all that stuff. But why do they do so? Because then things become more easy to understand, and this is a very, very elegant proof. I like that very, very much, and in your exam it's very likely that I try to ask questions, or at least one question, which deals with that stuff. So please don't skip that section, but work on that proof and work that you really understand that. It's very, very nice mathematics, and it's very fascinating how it is possible to model things, write it that way here, and then we get hold of the core of the things, and then we can prove that theorem. Very nice. I like that very, very much. Okay, the proof is done and the video is also done.